Okay, in this video I'm going to go through today's exam. So I'll go through each question. If you've got questions at the end of it, please come and see me in lab time. As I said, this is very much like the AP exam, and the questions for the AP exam, if you're getting more than 70%, you're well on track to getting a 5 in the AP exam. I know that some people will be disappointed with their scores today, but some people did really well as well. So some of you should be very happy. But everyone has made a good effort at it. Anyway, so number one, what's the average mass of 1 mole of naturally occurring pure carbon? How do we find this out? Very simple. We look at the periodic table. It will tell us that the average mass of one atom of carbon is 12.1 AMU. We convert this into grams because different isotopes of carbon are present, so that means that it's not 12 exactly. 12 is the most abundant though, and so the correct answer here is C. Question 2. A 5.0 sample of a pure compound contains hydrogen, carbon and nitrogen, and it contains 0.19 grams of hydrogen, 2.2 grams of carbon. Another smaller sample of this pure compound is analysed. Pure compound. So this means that the proportions must be exactly the same. The question is, how many grams of nitrogen should be found in a 2-gram sample? If we work out how many grams of nitrogen were in the 5-gram sample, we had 2.2 and 0.19. We're going to find out that there were 2.59, which means that it should be roughly half. If we look at the options, none of the options are close to that, except for B. Remembering the important principle here is that the pure sample, the ratios are going to be constant. Laboratory analysis produced the following mass percent data: 48.5% carbon, 3.9% hydrogen, and 47.5% oxygen. Find the empirical formula. First thing we need to do, find the molar weight of each one. We'll find that carbon is 12.01, hydrogen being just over 1, and oxygen being around 16. We divide each of the percents by this, which gives us 48.5 divided by around 12.01, giving us 4, 3.9 giving us 4, divided by 1 giving us 4, and 4.75 divided by 16 giving us 3. This means that the empirical formula is C4H4O3, and the correct answer here is C. How many moles are present in 2.1 times 10 to the 24 atoms of carbon? How many atoms are in 1 mole? Well, we should remember Avogadro's number, 6.022 times 10 to the 23 is 1 mole. So we can divide 2.1 times 10 to the 24 by 6.02 times 10 to the 23, giving us the answer of B. Nitrogen oxygen containing molecule is decomposed into its elements. It's found to contain 14 grams of nitrogen and 40 grams of oxygen. Find the empirical formula again below. So again, we look at the molar mass of each, 14 divided by nitrogen, which is 14, and 40 divided by 16, giving us 14 divided by 14 is 1, 40 divided by 16, giving us 2.5, giving us 2.5, which means that we need to multiply to get whole numbers. So nitrogen is 2, oxygen is 5. Correct answer is A. Multiple photoelectric effect experiments were conducted by applying a variety of visible wavelengths to a metal surface and recording the electrical current produced. Evidence from these experiments provided for which of the following claims? It provides that electromagnetic radiation exhibit wave-like characteristics. Not really. Electromagnetic radiation exhibiting wave-like characteristics would be shown by waves diffracting, waves refracting, waves following wave-like characteristics. Electromagnetic radiation exhibit particle-like characteristics. Well, here the electromagnetic radiation is causing electrons to move out of their current space and causing a current to flow. This does suggest a particle-like characteristic. Electrons have quantized energies in an atom. We're actually partly proving this. However, in order to prove this, we would need to show that some wavelengths produce electrical currents, some wavelengths don't produce electrical currents. Electrons behave like waves in an atom. This is not proved by this experiment. So the correct answer, the only thing that it actually proves, is B. An ion is an atom with an electric charge due to a gain or loss of an electron. Which of the following is the electron configuration for the common state of the most common alkali metal ion? Now, for it to be an alkali metal, it means it's in the group 1 of the periodic table, which means that it should have one in its not natural state should have one electron in the s layer. However, we're looking for the ion, so it won't have anything in that s layer. So the correct answer here is C. In a xenon atom, which atomic shell would experience the largest effective nuclear charge? The largest effective nuclear charge is always going to be the one closest to the nucleus, because you've got a large positive force and no shielding by any other electrons. So in this case, the answer would be A. All the rest, the effective nuclear charge is being reduced by the shielding effect of the interior shells. Consider an atom with the electron configuration 1s2, 2s2, 2p6, 3s2. Which successive ionization energy will be higher than the previous value? Which ion is this likely to make? Well, it's most likely to lose the two outermost s layer electrons. So these will be the two that will be most easily taken away. You'll easily take away the first one. You'll easily take away the second one. However, once you try to remove one from the complete second orbital, made up of the 2s2 and the 2p6, then it's going to be more difficult. So the conclusion is that this will make a 2+ ion, and it will mean that the third ionization energy will be significantly higher than the first and the second. An element with an electron configuration will have properties most similar to which element? Okay, it's got 3s1, so it's going to be in group 1. Which of these are in group 1? Well, helium's not, neon's not, cesium is, magnesium's not. So C is the correct answer. Looking at the photon electron spectrograph, what is the electron configuration for this element? Remember what this graph shows. On the y-axis, we've got the relative number of electrons, and on the x-axis, the energy levels. So, first energy level, the hardest to move all the electrons away is 1s. Then we've got 2s. Then we've got 2p. So we know we've got 3 electron orbitals. The height of these indicates the number of electrons. So if we assume this is 1s, it's going to be full, it's going to be 2. 2s, 2. This is half as high, the final one, which means that it's 2p1, meaning that the correct answer here is C. Looking at number 11, again a photon-electron spectrograph. So if you had difficulty with the last question, you probably had difficulty with this. And it's 2 marks gone really quickly, but it's 2 marks you'll never lose again because these are really very straightforward to understand. What have we got here? We got 1, 2 peaks in the graph, meaning that there's 2 orbitals. We can look at this one, there's twice the height of this one, so we're going to say there's 1s2, 2s1. So we're looking for the electron with the atomic number 3, which is lithium. List the elements in order of increasing atomic radii. Okay, so for this question we need to remember that atomic radii get larger as we move down the periodic table, but they also get smaller as we move right to left across the periodic table. So to do this, we can very quickly look at which is going to be the largest, which is furthest down. We look at Si, and we'll find that it's higher up the table than sodium and potassium. Potassium's the furthest down, sodium's above it, and silicon is in the same period as sodium, but far to the right. So that means that we're looking for answer B. 13. Why do elements in the same group have similar properties? Well, the reason that they have similar properties is that they have similar numbers of valence electrons. This means that they would likely undergo similar types of reactions. Looking at the options, though, we can rule several of these out. Members of the same group have similar effective nuclear charge. This isn't true. As we go down the group, we're starting out with much larger effective nuclear charges on their interior orbitals because we're having much bigger masses of protons, which mean much more positive to start with. Members of the same group share the same electron shielding. Again, this isn't true because as we move down the groups, we're increasing the numbers of orbitals that are having an effect. Members of the same group have similar electronegativity values, thus interacting with other electrons in the same way. No. Electronegativity increases as you move towards the right of the periodic table and also as you move up the periodic table. So as you're moving up the periodic table, despite the fact that they're in the same group, they're having different electronegativity values. So that means members of the same group share the same number and type of valence electrons. So the correct answer here is B. What evidence led scientists to discard the plum pudding model of the atom? And they led them to adopt a model with a tiny, dense, positively charged nucleus. Well, this came about because alpha particles, when they were shot at gold foil, most of them passed straight through the foil. This makes no sense if we've got a plum pudding model which is positive and negative charge all being in the same area. And a plum pudding, which is effectively a solid type idea. Instead, these particles can go straight through gold foil, meaning that there must be holes in it. Emissions, so looking at the other options, cathode ray bent towards a positively charged electric plate. Well, this is just demonstrating that cathode rays are electrons being affected by positive charges. Emissions spectral lines showing red, green, blue, and violet for the element hydrogen. This has absolutely nothing to do with it. This has to do with the fact that we have quantized emissions coming out of the element. So this is much further on. This is once we're looking at quantization of electron arrangements. And mathematical models plotting different shapes of orbitals. Again, this is much further on. This is when we're looking at the actual makeup of the orbitals, and we're getting towards, well, we're looking at Schrodinger's equation, and we've already accepted the idea of quantization. So the correct answer here is C. Which of the following statements is correct concerning atomic theory? With atomic theory, the 2s orbital in the hydrogen atom is larger than the 3s orbital in the same atom. Well, no, it's not going to be. Remember, 1s is closest to the nucleus, the 2s would be further away, the 3s would be further away again, so this makes no sense. The momentum of an electron in ground state atom is known. The location of the electron in the sp, d, and f orbital can be determined. No. The uncertainty principle means that as long as you know the momentum, you cannot know the electron's position. So this contradicts that. An orbital is the same as a Bohr orbit. No, Bohr had electrons orbiting round the electron in planetary type orbit. This we've shown is not necessarily the case. It's much more random, and the orbitals are just relative, the positions where we're most likely to find electrons. The third principal energy level has the sp and d sublevels. This is correct. So our answer is D. Besides concentration, what other factor could affect a visible spectrometry or colorimetry absorbance reading of a pure solution? Well, if you remember the Beer's law formula, it does include the width of the cuvette. This is a slightly tricky question because we always used a 1 centimeter cuvette, which meant that the value for this was always 1. But you could use a wider cuvette. The reason that would affect it is because they're passing through more of the solution. The temperature of the solution should have no effect. Completely filling the cuvette with solution should have no effect because we pass the light through the middle of the solution. And the length of time the solution is exposed to light, this should make no difference. The only time it would is if we've got a reaction actually taking place in the cuvette, and time is a factor in the reaction and changes in the solution. So the correct answer is A. Unknown pure substance was analysed with infrared and ultraviolet light. The sample absorbed infrared and not ultraviolet light. What information was gathered? Okay, going back to our first two experiments, we were using the spectrometer to analyze what light was absorbed, and the reason we could do this is because electron energies are quantized. So some electrons will jump up into the next layer and absorb the energy, others will not. This helps us to analyze the electron configuration of the atoms in the substance. The molar mass of the substance, we can't determine this by we can't determine this by just the spectrum. The way we were able to do it in the first couple of experiments was that we actually had standards to evaluate it against. The strength of the bonds in the substance, we're not making or breaking bonds in this situation, so this doesn't come into it. And the density of the substance, well, the density of the substance is purely its weight divided by its volume. So this doesn't help us at all. So the correct answer here is B. What is the concentration of NaO, sodium hydroxide solution, if it takes 12.5 mils of 0.1 hydrogen hydrochloric acid to titrate 25 mils of the sodium hydroxide? Okay, we're setting up a very simple moles times molarity times volume on one side is equal to molarity times volume on the other. So 12.5 times 1 is equal to 2.5 times 0.05. So we got yet another C. What is the concentration in molarity of lithium hydroxide prepared by dissolving 48.0 grams of solid in sufficient water to make 250 mils of solution? Okay, lithium hydroxide, we will find, has a molar mass of 24 grams, which means we're dissolving 2 moles in enough water to make 250 milliliters. 250 milliliters is only a quarter of a liter, so to find out the molarity, we must multiply 2 by 4, so we get B. Which of the following two bonds are most similar in polarity based on relative electronegativity differences? This is relative electronegativity differences. So we're looking for things that have relatively the same electronegativity. Again, electronegativity increases as we move to the right across the periodic table and to the top. So ideally we want to have things that are in the same groups because they will have the same differences between their electronegativity. The actual values of each electronegativity may be different. So the correct answer here is C. So aluminium and chlorine, and boron and fluoride. Fluorine. The numbers are different. Boron and fluorine is actually much more. Fluorine is much more electronegative than chlorine. However, boron is also much more electronegative than aluminium, and they end up being in a similar ratio. So the correct answer here is C. Which of the following compounds does not have trigonal planar geometry? Okay, so for this we need to draw our Lewis structures, and we're going to find out that the correct answer is C. Doing this is a case of adding up all the electrons, working out how many lone pairs you're going to have. If you've got lone pairs in both above and below, then we'll get trigonal planar geometry. If we don't, then we're going to end up with it being squashed down as C is, to make it trigonal pyramidal. It's going to be a pyramid. 22. How many unbonded pairs of electrons are found in a neutral atom of sulfur? Again, this is simply a case of working out your electron configuration, and you'll find that there are 2 unpaired electrons. two unbonded pairs of electrons. Next up, analyze the graph above. The equivalence point, so looking at a titration, we know that point A is very acidic. Point B, we've clearly added some base. At point C, we're passing through the point where it's turning from acid to base. And at point D is then very basic. So the correct answer here is C. Consider the reaction. We're looking at zinc sulfide and oxygen turning into zinc oxide and sulfur dioxide. We're going to heat up 50 grams of zinc sulfide in an open vessel until no further weight loss is observed. So until there is no more reaction taking place. Looking at the balanced equation, we're looking for the mass of zinc oxide being produced. The balanced equation shows 2 and 2, meaning that 1 mole of this will give us 1 mole of this. 50 grams of zinc sulfide. 1 mole of zinc sulfide is 97. Or approximately 97, so 50 over 97 should be equal to X over the molar mass of zinc oxide, which is approximately 80. It's about 50%. We can tell that this is coming close to 40, so we're tempted to put down B. However, the reaction only has an 80% yield, so it doesn't work to the true theoretical value, which means that we then have to multiply our 40 by 80%, giving us an answer of A. Final question. Sample of 25 milliliter 0.12 molar barium hydroxide is titrated with 0.15 molar hydrogen bromide. What volume of hydrobromic acid is needed to completely neutralize the barium hydroxide? Important thing to remember here is the 2. So there are going to be 2 moles of hydroxide produced for each mole of barium hydroxide that is used, which means we can effectively multiply 0.12 by 2 to give us 0.24 moles of hydroxide ions, multiplied by 25 milliliters is equal to 0.15 times X. X in this case is 40. And so our final answer is B. Okay, so that's us through our review of the test. As I said, if there are areas that you look at and you're thinking, oh, I really don't understand this, please book up lab appointments. If there aren't areas that you're still confused about, and yet you're still disappointed with your score, don't be. This is simply a matter of practicing. On the AP exam, you need to be able to look at these questions and think, what do I actually know? They won't always be asking you something straight from the textbook. And yeah, this is at the end of term 1. Well done, everyone. If you look at your first lab report and you look at your last lab report, you'll see how much you've improved in that area. If you look at this test and you listen to the answers and you understand all the answers, then you've improved massively there too. All we need to do is keep practicing this. Please make sure that you're watching all the videos, because we're not doing much lecturing in class, and you need to be making sure that you're doing the work outside of class. Anyway, Thank you, and have a good night.